With all of that said, I want to welcome Jeff Zweerink, who is with us today from Los Angeles. And he's going to talk about recent discoveries, very recent discoveries made through the James Webb Telescope and what the implications are for science and for faith. Jeff obtained a BS in physics and a PhD in astrophysics from Iowa State University, where he focused his study on gamma rays, messengers from distant black holes and neutron stars. Upon completing his education, he taught at Loras College in Dubuque, Iowa, before pursuing postdoctoral research on the West Coast at the University of California, Riverside. And I don't know why he stayed on the West Coast and didn't come back to the Midwest, but he didn't. More recently, he has had a research faculty position at UCLA, where he conducted research using STACEE and VERITAS gamma ray telescopes, but more recently and currently works on the GAPS program, which is a balloon experiment seeking to detect dark matter, which might take him to Antarctica. But for now, he's not in Antarctica, even though it may feel that way here in Chicago. He's in sunny Los Angeles, and we are really looking forward to this presentation from Jeff.
Well, thank you. I appreciate being here. And I can tell you it's not quite as sunny, which is why my camera is so dark. Normally, I get enough light coming in from my window that it illuminates me, but it's overcast today. And so I don't have as much light. And I can answer your question of why did he stay out on the East or West Coast instead of coming back to the Midwest? And it was because God kept saying, no, I want you out here. No, I want you out here. I can attest and have spoken many times where I've said I didn't want to move out to the East Coast or West Coast, especially California. And what I have found is that it's far more important to follow where God says to go than it is to follow my wishes. Because though I have family in the Midwest and would love to move back there, this is where God has us, and this is home. And so have a nice opportunity to live out here. And I got to say, one of the things that I really enjoy and find amusing about being out here is that my folks still live in the Midwest and I live out on the coast, and you have different catastrophes, if you will. I mean, we have wildfires, we have flooding, we have earthquakes out here. Midwest, you have storms, occasional tornadoes, those sorts of things. And so it's really interesting because every now and again, something that happens here will make it on the news in the Midwest, or something that happens in the Midwest will make it on the news out here. And multiple times I've had this conversation with my mom. You know, she calls out and says, hey, I heard that it's, fires out there. And it's like, yeah, there was fires burned across the mountain up in the hills behind us, that it's a big deal, but ordinary out here. And the coverage always makes it sound like the world is ending. And I've had a couple of times where storms are moving through the Midwest and I call back and it's like, yeah, it's raining here. So I have learned to take the weather coverage at the very minimum on the news with a grain of salt. But that's not why we're here today. We are here to talk about the James Webb Telescope. And I'm going to go ahead and share my screen here. Because I have some slides that I think would be interesting and good to show. And one of the things that I want to just start off saying is that as we do science, as we go out and try and understand creation, one of the things that I have recognized to be true is that a lot of the very biggest discoveries don't typically come from you go into the lab, you work out your calculations, you do some intricate experiment and you get a new result. It's that you build better instruments that can just see more stuff and are more sensitive. And that's one of the things that I'm really excited about the James Webb Space Telescope, that I would love to say, here's what we found and here's what we're going to find. But a lot of what I think we're going to find is, as we go out and use it, we're just going to see stuff that we didn't know was there before. And that will help us understand how this universe works. And what I'm going to do today is just show you some of the things that the Webb has seen already. I'm going to show you some of what it's capable of, how it works, because I think it's important to be able to compare or put the James Webb Telescope in the context of all the other telescopes that we have and then specifically address some of the concerns that it has raised about the validity of Big Bang cosmology. Because I think from a physics astronomy perspective, I think that is one of the most powerful pieces of evidence of the truth of Christianity, is that what Christianity describes about the universe on the largest scales and what we found scientifically line up very, very well. And so with that, I just wanted to start by showing some of the images that it has come in. And this, you probably may or may not recognize this image as a similar one from the Hubble Space Telescope, but this is just a spectacular. This is the sort of thing you would frame and put on the wall of your house in your living room as a conversation piece. And this is not, ooh, we've got to smooth it out and make it look better. This is what the image looks like coming from the telescope itself. And this is enormous in scale. I may talk a little bit about it more later, but you'll notice that as you look around the edges of all of these things, there are these little bumps and kind of spires that stick off. Each one of those little bumps and spires is actually a star that is being formed. Like you can see one right here that you can actually see the star in the end glowing, because one of the things the Webb telescope does is looks through the dust and allows you to see through the clouds. And so this iconic image from the 90s and 2000s, where Hubble found or looked at the pillars of creation, the Eagle Nebula, Webb has gone out, and what Hubble can do, it equally says, wow, this is just a spectacular image. This is another image. This is a galaxy. It's called IC 5332. Astronomers are not known for having particularly creative names for things. I know almost every name that's out there is IC. C almost always stands for catalog. I'm not sure what I stands for. And then 5332 is the number of the object in the catalog. But this is a galaxy, and what you'll notice is that this doesn't look anything like the galaxies that we're used to seeing when we see images from telescopes. And there's a reason for that, which I'll articulate in a little bit. But again, I am just impressed by the detail that shows up in the picture, the beauty that shows up in the image, the intricacy, it's just kind of otherworldly when you're looking at images like this, especially what we've been conditioned to see and what we think of how the universe works. And that's one of the things that the Webb is bringing us, is just a picture into the beauty, spectacular grandeur of God's creation, but also insight into how it works that we weren't able to get before. Even more closer or local to home, this is a picture of Neptune as we shine the James Webb at it. And you can see very clearly the rings that are around Neptune. All four of the gas giants have rings. Jupiter has a ring. Saturn obviously has rings. But both Uranus and Neptune have rings. And these rings just stand out. And there's kind of this otherworldly, ghost-like view to this image, which I find pretty fascinating, that, again, the Webb telescope is just going to bring us new ways of looking at things, a beauty and an intrigue about it, but a new way of looking at things, data that we didn't have before that gives us better insight and understanding of how creation works. This was one of the new images that the Webb found that I found particularly fascinating, because this is a star in our galaxy. It's actually not a star. It's called Wolf-Rayet 140. And that's a particular class of stars. And this particular star, that Wolf-Rayet star, it's a binary star. And these two stars, they're pretty massive. I think these tend to be 10 solar masses and up. Wolf-Rayet stars do, because they have enormous winds that blow off of them. And these two stars, every 8 years, they get very close to one another, and the winds from the two stars get compressed, and they end up forming a ring of dust. And that happens every 8 years. And so if you look on this, you can see there's a ring there, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And actually 17, maybe even 18 rings out there. So think about that. 18 rings every 8 years. We're looking at 100 years of history just in the rings that are there. And before we had the Webb, we could see 1, 2, maybe 3 of those rings at best. And so again, it's just what the Webb brings us is stuff that we couldn't see before. And I'm just, I want you to see the detail and the sophisticated and the clarity and the sensitivity of the image, but also just kind of the beauty and the grandeur that come out of seeing God's creation. And I find that remarkable because these are things that are thousands of light years away. This one's 5,000 light years away from us. The Eagle Nebula, I think, is 8,000 light years away, which is, about a third of the way towards the galactic center. IC 5332, that's a galaxy in and of its own right, somewhere very distant. So these distant objects, these telescopes like the Webb and the Hubble did before, bring us closer, or bring those objects closer to us so that we can see what's going on and just kind of sometimes just stand in awe of what we can find and see. And so I really find what the Webb is bringing fascinating. One other thing I will point out is that you can actually go make your own images. Virtually all of the James Webb data is freely available. There are portals that allow you to access the data. You can go in and say, I want this kind of data at this wavelength and have it be brought in. And there are tools to edit and make them. And so I'm showing this particular article, and I'm drawing a blank. I want to say this was published in Nature, but it was either Nature or Science, one of those journals, where this gal Elizabeth Howell is a citizen, or sorry, Elizabeth Howell wrote the article. Judy Schmidt was the person who was doing this. She has just kind of made it a practice to go in and get the data from the telescope, kind of massage it, and you can make your own images. And I know there are people who are artistic and like to do that. And so, I just kind of wanted to let this object be known because it is one of those images where someone who's not working with the Webb data, they're not the scientist who wants to know what's going on. They've just gone in and said, hey, I want to work with the data and see what kind of images I can make. And this one, it's called the Phantom Galaxy. That's a pretty remarkable image. Again, doesn't look, you see the spiral structure like we're used to seeing in galaxies, but there's a very different nature to the way this data shows up in the Webb. And so you can actually, in this article, she lays out the process of how she goes about making them so that you can get started in doing that. So I want to make sure that people know that there's this data available. I actually have gone and downloaded some of the data and pulled it in and kind of made a preliminary image. It's really not that hard to do. I would encourage you to check that out and go doing it. It gets more people engaged in looking at the science itself. One thing that is true that I think it's very important to keep in mind is that we think, oh, the Webb is the successor to the Hubble Space Telescope. And we think, that there's this implication that comes along with that the James Webb is just a more sensitive version of the Hubble Space Telescope. But there are some very important differences in these telescopes that we need to keep in mind as we're talking about it. And one of those differences is that the Hubble Space Telescope was designed to be a visible, or to work in the visible range of the electromagnetic spectrum. So it works in the visible and ultraviolet range of the electromagnetic spectrum. There are some technological reasons why it was chosen to work there, not the least of which is that you have to put less telescope controls on moderating the environment around the telescope because visible light works well on mirrors, and there's not a lot that will block it out once it gets into the telescope. But it's designed to work in the visible and ultraviolet, and also because most of the stuff it wanted to see was going to be in the visible and ultraviolet range. In contrast, the James Webb Space Telescope is built to work in the infrared. And the reason why it's built to work in the infrared is that as you look farther and farther and farther away, the light from the objects you want to see is shifted more and more into the infrared. And so part of the reason that the Hubble Space Telescope can only see so far away is because the stuff that it's designed to look at, the light from those objects that are more and more distant gets increasingly shifted into the infrared, and the Hubble Space Telescope just isn't sensitive to that. And so they built the James Webb Space Telescope and designed it to be sensitive to the infrared because that will allow us to see further away. And because you're looking in the infrared, it actually allows you to see through stuff that the Hubble Space Telescope would just be able to see the surface. The Webb will be able to see much deeper into that. So you got to remember, the Hubble telescope, what you're seeing is visible and ultraviolet light. James Webb, what you're seeing is infrared light. One of the other implications of that is that when you're looking at an image from the Hubble Space Telescope, that's actually what it would look like to us, because our eyes see light in the visible part of the spectrum. That's why it's called the visible part of the spectrum. With the James Webb, every image you see looks kind of like it ought to be a visible image, but it's actually the infrared translated into the visible light. That's why these galaxies we look at, for example, that I'm going to show you, look so different, is that we're not used to seeing them in infrared light. If our eyes were sensitive to infrared light, this is what galaxies would look like. Our eyes are sensitive to visible light, so we see them very differently. And so if you now go out and ask the question, how do Hubble and Webb compare to one another? This is an image of the Carina Nebula, something in our galaxy. It's again, one of those iconic images from the Hubble Space Telescope. And you can see on the image, you can see, sorry, finding buttons on my remote here. You can see, you know, these little bumps, and there's divots, there's this wave of gas, and there's gas emanating off of it. And, you know, there's just lots of things you can see in there. Well, the James Webb went and looked at the same region of space, and this is what that same region of space looks like. Now, recognize again that this is in infrared, not visible, but you can see that we're kind of largely looking at the same things here. You can see this star is that star there. There's these two down there. That's those two there. You know, you got this little triangle. There's a little triangle. So you can see this is the same image or the same place, obviously. But, you know, here's this one star that shows up very bright in infrared, but has virtually no counterpart, or maybe it's that one down there. It's very dim when you're looking at it in the visible. Also notice that there is just this panoply of stars that are visible here. And that's because what the Hubble sees as it starts to encounter dust, that dust reflects the visible light back to us, whereas the James Webb kind of sees through the dust and sees what's going on behind the dust. But the main thing I want to point out here is just notice how much better resolution the James Webb Space Telescope has. In part, so it's two things there. One is that it's got better resolution, and two, it sees different things because it looks at the infrared instead of the visible. So it will see through the stuff where the visible light will get reflected off the dust. It can see through the dust to see what's going on behind it. And this is, if we go back to IC55 or IC5332, if you look on the left there, that is the James Webb image. If you look on the right, that is the Hubble Space Telescope image. Hubble Space Telescope image, again, that's that normal, what we expect. You see the spiral structure, you see that kind of dusty filaments in there. You can see the spiral arms, clusters of star formation. Whereas really what you're looking at in the Webb, you're looking at where is all the gas distributed. That's what you're seeing here. You're seeing how there are these pockets where the gas has been collapsed down into stars and it's all exhausted. And you're just seeing the same object with a different pair of eyes. And you can see a lot different information as a result of that. So it gives us a new picture. The Webb is giving us a new picture into how the universe works and operates. This is one of my favorite images, and this is the Phantom Galaxy that Judy Schmidt was one of the ones who developed the image for it. And again, you look at this, you can see that it's a galaxy. There's this deep blue core in the middle. There's the spiral structure. You can see the spiral arms. There's the gaps in the arms around them. And because we're looking at this with infrared light, again, we're seeing things different. We're seeing it differently than the Hubble Space Telescope because it looks invisible. We're getting different pieces of information. You can see where all these clusters of stars are being formed in there. You can see where the gas, where there's just these voids in the structure of the galactic plane. You can see the deep blue where a number of older stars, these brighter stars show up. And why that's interesting is because if you now take the Hubble image, which is on the left, you take the Webb image, which is on the right, and you can combine them, and you can see that there are these pockets that show up on the pockets that show up on the Webb are actually, you can see how they correlate with what's going on in the optical. And by putting the two together, you get a much better picture.
Hi, everybody.
There's a place where that shows up even better. That's one of the tools
Yeah.
that the Webb telescope is going to do for us, is that it allows us to look at the same things in different wavelengths. And that's going to give us a lot of insight into what's going on. But again, some of these, I just want to keep the images up there because they're impressive to look at. And I say that as someone who's not particularly artistically inclined, but I'm looking and it's like, wow, this is just really cool. So here, if we go look at the Eagle Nebula, you see the Hubble image on the left there. And I learned a new word when I was doing the research for this, because you look at the image from the Webb and it is diaphanous. I like that word, diaphanous. It just looks almost ghost-like, like it almost isn't half there. This almost looks on the Hubble Space Telescope, it looks like there's this solid structure that's growing out. I mean, you can see that it's gaseous there, but it almost looks like if you were flying a plane and, well, you couldn't fly a plane because there's no air out there, but if you're flying a rocket, you might bump into something and have a problem. Whereas you look at that with the Webb and, kind of looks like one of those things you could swipe your hand through and it would just dissipate and be gone. Because the Hubble sees the gas, gives a real definitive edge to things, whereas the James Webb is looking at things that give off infrared light, and that is just more nebulous in this region. And so some of that is, again, we're taking infrared images, translating them into the visible, and they just look ghostly because we don't see things in the infrared. And so it makes things look very, very different to us. One of the other big differences with the James Webb Space Telescope, and it's driven by the fact that the NASA wanted to build an instrument capable of working with infrared light, is that it is located very, very differently than the Hubble Space Telescope. With Hubble, it's actually in a low Earth orbit, about 600 kilometers above the Earth, orbits around. It is an instrument that we can, when we were flying the space shuttle, take the space shuttle up, pull the Hubble into the bay. Hubble was designed to fit inside the bay of the space shuttle so that it could be worked on, so that it could be launched. Which means that if Hubble had a problem, in principle, we could go up and fix it. In fact, when the Hubble was first launched, after it went through its kind of initial paces, we looked out and it was, all the images were fuzzy compared to what we were expecting. Now, it was still the best telescope that we had, but it was fuzzy compared to what we were expecting. And what they realized is that the Hubble Space Telescope, the mirror, had been perfectly ground to the wrong specifications. And you'd love to think that this was a very subtle, or how do we make this kind of problem? What ultimately was the cause of that was that there was a technology they were using to measure the shape of the mirror, and there's a detector that they put on top of a rod. The rod was put in upside down, and that just changed the distance just a little bit. So Hubble is perfectly ground to the wrong specifications. Now, the cool thing about that is that now that we know what's wrong, now once scientists figured out what was wrong with it, they could go in and build a correction for it. And so they were able to correct the optics. They did lose a little bit of its designed capacity, but it is exceeded what astronomers thought they were going to be able to get from the Hubble. And it's been producing fantastic images for more than 2 decades now. All that to say, with the Hubble, we could go up and fix things if they went wrong. With the Webb, because it's looking at infrared light, in order to see infrared light, the background for infrared light, or what gives the background for infrared light, is heat. I don't know if you've ever been to one of those science museums where they have those thermal cameras and you go walk in front of them and they're typically purple and the bright things are orange. Well, that's a camera that is working in the infrared. And so where there's heat, that's background, or causes the background to increase for any sort of instrument you're working. And so one of the things that they have to do with the Webb is get it very, very, very cold. And to do that, you want to move it as far away from the Earth, because the Earth is pretty warm. And so what they've done is actually located the James Webb Space Telescope 1.5 million kilometers from the Earth. And it's a little hard to see, but if you come down here, so here's the sun right in the middle of this part of the object. Here's the Earth. It is out here at the L2, it's called the L2 Lagrange point, way out here. Sorry, mine's on the edge here. I'm going to move my scale. So maybe that helps you see. It's out here at this Lagrange point, and there are certain places like this Lagrange point is the place where the gravitational pull of the sun and the gravitational pull of the Earth are equal. So something there experiences no net gravitational pull, and it will just orbit there. Well, with L2, there's a similar sort of phenomena that it will always orbit. The sun will be there, the Earth will be there, and the L2 point is out there. So the James Webb Space Telescope orbits right around the L2 point, so that the Earth is blocking the light from the sun that would be hitting the James Webb. It moves the James Webb far enough away from the Earth that the heat radiated from the Earth doesn't interfere with its background. And that's part of what allows it to see all the infrared light that allows it to take all these spectacular images. What that does mean is that we can never go out and work on it. And so if you think what that means for the James Webb Telescope, I'll give you a little bit of details, in terms of size of mirror and things like that. But the mirror is about 6 meters in diameter. It's got a sun shield that is about the size of a tennis court. All of this has to fold up and fit inside a rocket. You launch the rocket, it comes out of the rocket, and as it's traveling through space, it unfolds in the coldness of space down near absolute zero to make a mirror that is optically, optical quality mirror, which has precision on the order of nanometers in terms of the mirror, in terms of all the locations of things. And it does that all automatically with no human intervention once it's launched. This is a technological marvel that we were able to build this. And so there are multiple redundant systems. I mean, there's just the engineering of this is fascinating. And I could probably give a whole talk on what do they do to make all of this work. But because this is so far away, it really gives a measure of the ingenuity that goes into building this class of instrument. Again, it works in the infrared. Hubble works in the visible range. There are other telescopes that work in the X-rays, gamma rays, microwave, all sorts of different wavelengths. But because it is so far away from, or because it works in the infrared, and it is so cold. And again, just to get one other thing about the technological masterpiece that it is that it's working down, minus 400 degrees Fahrenheit. On the sun side of the shield, so there's this sun shield that keeps the instrument cold, or shields the instrument from the sun. On the sun side, it's almost hot enough you could boil water. 3 meters away, it's so cold that water would freeze and almost never warm up. It's, again, well over 400 degrees difference in Fahrenheit. And as it uses that infrared light, we can now look at things like the Cartwheel Galaxy. And this is actually one of the first objects that I did any work on. Back when I was an undergrad, I worked at Iowa State, I was going to Iowa State University, and one of the fellows that I worked with in undergrad, one of the classes I had, he and a colleague were working on the Cartwheel Galaxy. And one of the things they were trying to understand is, how does a galaxy like this form? And it turns out there's an interaction. You see that there are these 3 galaxies that are around it. What happens is, if you take a spiral type disk galaxy and you have another galaxy pass right through the middle of it, it will cause interactions in all the gas. There'll be a shock wave that propagates out, and you'll get this central bulge, which has a lot of stars. You'll get a ring of stars being formed as it propagates out, and you'll get these filament arms that extend between the two. And so we were doing computer simulations back before computers were nearly as powerful as they are today, of what does the collision look like that gives a galaxy like the Cartwheel Galaxy. Now, this image is actually, again, it's a composite of the Webb images, and there's this is one of the near infrared cameras. This is one of the Webb cameras. There's another Webb camera on there. I'm sorry. This is actually the visible part of it. So you can see the blue star, the blue region around, that's where all these new stars are being formed. You can see the central bulge there. That's where stars have formed much further in the past, and they've turned more yellow. But when you now add in, the infrared, which you can see kind of some of the older red stars and the filaments that go in there, you get an image that, putting all of this information together, gives, again, a more complete picture of what's going on. And one of the great powers of the Hubble Space Telescope and the Chandra Space Telescope, which was an X-ray telescope built by NASA, and the Fermi Gamma Ray Telescope, is that all of these telescopes work in different wavelengths. As you use them to observe the same object, you get a whole bunch of different eyes on the same object, and that gives you a lot more information, allows you to get a much, much better understanding of what's going on. And that is certainly true just here with the Cartwheel Galaxy. Again, this was produced by a couple of my professors back when I was in college at Iowa State. Another key difference, you've got different wavelength that Webb works at compared to Hubble. There's a different location of where they are, but the mirror size is different. Why that's important, and this leads directly to the sensitivity that the James Webb Space Telescope has, is that the size of the mirror determines your resolution. The larger the mirror, the better you can resolve things. It's just a simple geometry type thing. And so the radius of the James Webb is almost 3 times larger than the radius of the Hubble primary mirror. And it not only does it have a larger mirror, so you get better resolution, but you also get a whole lot more mirror area, which means you collect a lot more photons. And both of those things lead to a greater sensitivity. And what you see there, going back to a little bit of the technological aspect, is that there are, I think, 19 segments, maybe 18. I don't think there's the one in the middle there. Different segments of the mirror, those all folded up into, like 3 or 4 square meters tops to fit into a rocket. And then as Webb is flying out to its location at the L2 Lagrange point, these all unfold into this configuration. And the fact that that does that in the cold of space, I don't know if you've ever worked inside a refrigerator. Imagine going into a freezer at your local grocery store where they keep the meat and everything. Stuff just tends to not work well there because it's cold, and cold makes things tighter, more rigid. Well, this is doing it out in the recesses of space, which makes that freezer seem like a boiling sauna. And it worked flawlessly. It was incredible. But because it has such a large mirror area, it can see further back in space. So notice here, this is the axis here. You got the Big Bang over here on the right. Our time is way out here, right at the edge of this curved structure, the visible structure there. And if you look at the Hubble Space Telescope, Chandra Deep Field, they see back here, again, impressive, but the James Webb can look even further back, getting close to the dark ages. This is where there were no stars, no galaxies, and this is right at the edge of when stars were being formed. And you can see that the James Webb is able to do that because it's got a larger mirror area, which allows it to see more distant objects, things that would be too dim for the Hubble to see, it can see. It can resolve things further away because things that the Hubble couldn't make out, because it's got a smaller mirror, the James Webb has a larger mirror. Because it's looking in the infrared, it can see light that would be redshifted out of Hubble's visible range or sensitive range the James Webb was built to see. And so it can see further and further back in space, and it's able to see some of the first galaxies that were formed. Hopefully, as time goes on and we're able to get 20, 30 years of data, we'll be able to see and actually come across some of the first stars that were formed. Because that's an area of astronomy or the development of the universe where we think we have a good idea what's happened, but we don't actually know because we don't have any data from the first stars. We can't see them. They burn pretty quickly and they're gone. And so being able to actually see them would help us provide observational evidence to a key piece of how we think the universe developed from the Big Bang up to today. But it doesn't just look farther away. Because it's got greater sensitivity and better resolution, it can actually find exoplanets very well. And so here are, again, the Webb has been up for on the order of a year, maybe a little less than that. And in that time, it has already found a couple of exoplanets or it's gone out and looked at some exoplanets, places where we knew they were. And again, what happens with an or where you're finding them by the transit is where you've got a geometry where your telescope is looking at a star and the planets pass in front of the star. And so as a result, here's the light from the star. The light will dip because the planet is blocking out that light, and then it comes back up. And you can see there that we've found WASP 996b, and there's WASP 39b. Again, just for the naming there, WASP is the particular instrument, 3969, that's the number of object in there. A is always the star, B, C, D, E, F, G, and so on are the planets that are there. And so you can see that the Webb can very easily see planets using this technique. What is interesting is not so much that we knew the Webb could find exoplanets like this. It's not too hard to build a telescope that can find transiting planets. But as the planet begins to transit, if there's any sort of atmosphere, there might be information about the atmosphere in this part of the light curve. And so astronomers have taken the Webb and specifically looked at that, looking at WASP 39b. What they're able to detect is that there was carbon dioxide in the atmosphere of that planet. And if you look at WASP 96b, there are various water lines that the Webb telescope was able to handle. Now, just to put this in context, both of these planets are Jupiter-sized planets. These are not Earth-like planets, but it shows what the Webb telescope is going to be able to do as it, in conjunction with other objects, looks at an exoplanet and says, hey, what can we tell about the planet? We're able to start measuring what is the composition of the atmospheres on these planets. That is going to be a key feature of evaluating whether a planet's habitable or not. Because right now, all we have is the size of the planet, the orbit of its radius, or the radius of its orbit, and the type of star that it orbits. That's really the information we have. It's kind of like saying, all right, I've got this distant light about a mile away. I'm going to have people pass in front, and I want you to choose an NBA caliber team. You just don't have the information you need to evaluate that. Well, if we want to know whether a planet's habitable or not, that's kind of the situation we're in, of trying to choose the NBA team with this very little information. Webb is going to give us more information so that we can actually assess more credibly whether a planet might be genuinely habitable or not. And even more exciting than just looking at some of the gas in the transits is that they were able to take the James Webb, look at a particular object. This is Hipparcos 65426b. Again, love astronomers' original names. But they were able to find there's a coronagraph, sorry, let me say that properly. The Webb telescope is designed as a coronagraph, which means it's got something that it can use to block out the light from the star and then see the light around. And what you're able to see in these 4 images is the star location is located there. It's blocked out, and you can see the light from the planet in all 4 of these different detectors. There's the NIRCam, different wavelengths, and then the MIRI, which has 2 different wavelengths. It's able to see the actual light from the planet itself. This is not blocking the starlight. This is not starlight passing through the atmosphere. This is the light being radiated from the planet itself. Now, again, this is a 6 to 8 Jupiter mass planet, so this is not a habitable planet by any stretch. It's only 10 to 15 or 15 to 20 million years old, which is where stars tend to radiate most in the infrared. And just for scale, it's about 100 astronomical units from its host star, whereas Earth is 1 astronomical unit from the sun, and Jupiter is 5 astronomical units from the sun. So this planet is very far away from its star. But what it tells, the information it gives is that the Webb is capable of seeing lights from the planets themselves, and in special circumstances like stars that are close to us 4 or 10 light years away, we can see down to Saturn, Uranus, and maybe even Earth-sized planets orbiting around those stars. That's what this sort of information tells us. The Webb telescope is working very well in its capacity, even as scientists are still running it through the works to make sure that it's calibrated properly and all of that. It is working extremely well. In fact, it's exceeding our expectations. And this is one of the first images that came out. It's kind of the deep field version of Webb's observations. This is a galaxy cluster. It's called SMACS 0723. Made 12.5 hours of observation. Now that's a comparison to the Hubble Ultra Deep Field, which took 12 days of observation. So instead of 1 million seconds, which is 12 days, this is maybe a couple 100,000 seconds. So about 10 times less observing time is what it took to see kind of something equivalent to what the Hubble Space Telescope was with 12 days worth of observation. And we're seeing galaxies that date back to 400 million years after the Big Bang, maybe as far back as 250 million years. This is one of the things that the Webb was designed to do, and it's starting to show that it's capable of doing that. And what caused a lot of stir is that some of these galaxies are more massive than we thought they would be, and they're more complex than what they were expected to be. So with Hubble, we're, leading up to everything Hubble measured, the picture of galaxy formation is that galaxies start out some sort of cluster, there's gas, it clumps up, it grows larger and larger, you get more and more structure in it, and all of that takes time. Well, that would mean that the types of galaxies that the Webb would see would be smaller galaxies with less well-developed structure in it. So here we are seeing galaxies with Webb that are massive and far more complex than what we expected. And when that happened, there was some fairly popular, a large popular discussion of maybe the Big Bang's wrong, because Big Bang says, all right, we expect these galaxies to be small, they grow larger, and that's not what we're seeing. We're seeing galaxies far larger than we expect. We're seeing more complex galaxies than we expect. And so there was this claim that maybe the Big Bang's wrong, that there's a better way to look at it. We need to look at this alternative model. And so what I want to spend now is about the last 5, maybe 10 minutes, depending, just kind of addressing what's going on there and how do we think about that? Because one of the things to remember in this is that the evidence for Big Bang cosmology doesn't come from shapes of galaxies and what we see. The evidence for Big Bang cosmology is that we live in an expanding universe. And 100 years ago, astronomers, Hubble and Lemaitre and everything, were able to work out and figure out that as distance grows, distance is here on the x-axis, the velocity of the galaxy we look at is getting larger. And when Hubble was able to take Vespo-Slipher's data and other data that was around and put it together, there's some little bit of a side note. Hubble tended to steal other people's data and present it as his own without giving credit. And so I want to make sure, I'm going to call this a Hubble diagram, but there's a whole lot more people that I think should get credit. Vespo-Slipher is one of them because he was the one working on measuring the redshifts. What we see is that the farther away a galaxy is, the faster it's moving away from us. And that extends not just to the 1 or 2 megaparsecs that the data in this plot shows, which is, the Andromeda galaxies out here at about 2/3 of a megaparsec. So this is all pretty local. When we look out 500 megaparsecs, getting out, a significant fraction of the way across the universe, we see that, lo and behold, this relationship holds. And even as we look out further and further, this is same plot differently so that we can see whether there's dark energy or not. And if you look at where a Z of 0.1, just to relate the images on the right with the image on the left, this is where a Z of 0.1 is. And so you see, we've actually got a whole bunch of data way up out here. So it really is the case that we live in a universe where the farther a galaxy is away, the faster it's moving away. What James Webb has to say doesn't bear on this information at all. All of this information is still true. We live in a universe that is expanding. We look at the cosmic microwave background radiation and we see evidence of the universe being much hotter in the past. And as we look at the details of that cosmic microwave background radiation, we see the fluctuations in density that allow galaxies and clusters and structure to form. And all of this shows that we live in a flat universe with this much mass and this much density. All of this is from the cosmic microwave background radiation, which the James Webb Space Telescope has no capacity to look at and investigate. So to claim that the James Webb Telescope is showing that the Big Bang doesn't happen is really an oversimplification at best, but it just misses that there's what the Webb is capable of observing doesn't weigh in on the most basic pieces of evidence pointing towards Big Bang cosmology. Now, what the Webb does show is that there are galaxies that are larger and more complex than we expected. And why this made such a big stink is that there was a fellow, James Lerner, who's got a physics background. I don't think he has a PhD, but he's got a physics background, a pretty talented engineer, works in plasmas, a very, nothing, no pejorative about it. He's someone who's bright and who works in plasma and has a physics background. He published an alternative model to the Big Bang back in the 90s, where he was arguing that gravity is not what is driving the dynamics of the universe. It's actually electromagnetism in the forms of plasmas. And you get plasmas are what causes galaxies to form. Plasmas are what causes stars to form. And we know plasmas are involved with that. But the question is, are plasmas driving the dynamics of the universe, or is gravity driving the dynamics of the universe? And in his plasma cosmology, galaxies grow rapidly and get large and complex very rapidly. And so he's saying, ooh, we're finding galaxies that are larger and more complex. That shows that plasma cosmology is correct. But he doesn't at all, these new discoveries don't at all address the biggest pieces of evidence in support of Big Bang cosmology is that the farther away a galaxy is, the faster it's moving away, which implies an expanding universe, and that the cosmic microwave background radiation shows that our universe was much hotter in the past and has the necessary fluctuations that allow structure to form in our universe. And so as I was looking into this, because again, it was a pretty popular thing, I wrote an article about it on our website, Do the James Webb Telescope Images Show the Big Bang Didn't Happen? And in that article, I point out a few things. One is that Lerner's claims have been around for 20 years. And 20 years ago, when they came out, scientists didn't say, oh, that's stupid, we're not gonna look at this. They said, okay, here are your claims. Let's analyze them and look at them. And those claims have been addressed and rebutted very well. There's a colleague of mine at UCLA, Ned Wright, who's got an article on the UCLA website that shows how his claims the claims that he makes that plasmas are what's driving things instead of gravity don't stand up well under scrutiny. In fact, the better explanation is that gravity does it. So his claims are not new. He's just using this new piece of evidence, these new discoveries to bring more publicity to something that had been around and that the scientific community has largely addressed and said, no, that's not a good way to look at things, or that's not the best way to look at things at the very least. The other thing that is important about, or that I think is important to keep in context as we're looking at Lerner's claims, is that what he's saying is, okay, we've got these galaxies that are too complex and too large. What do we do with that? In my tenure as an astronomer, the idea that there are things out there that are at first blush appear not to work is just pretty commonplace. When I was in undergraduate, astronomers had two techniques of measuring the age of the universe. One said it was 10 billion years old, one said it was 20 billion years old. They didn't say, well, we can't find this out, we're just wrong. It's like, no, that discrepancy caused them to say, what do we need to do to resolve this and figure out what's right? Well, in the meantime, they've done more work on both techniques. They built the Hubble Space Telescope. One of its key goals was to resolve this issue. And it turns out the answer's not 10, it's not 20, it's 14. But even with getting it down to 14, now there's a discrepancy between the galaxy motion and the date you get from the cosmic microwave background. One says 14 and one says 13. So what used to be 10 and 20, we've narrowed down now. There's still a discrepancy between 13 and 14. And that discrepancy only showed up as we could come in and say, no, it's 13.8 instead of 13 plus or minus, half a billion. So this idea that there are anomalies or things that are they don't fit uncomfortably or appear to work. You can't have it be 13 and 14. Something's clearly wrong. Those have always driven us to gain a better understanding. And so what's going on here is that we're finding galaxies that are bigger and more complex than we expected. What will happen is people go say, all right, what do we need to do to our understanding of galaxy formation? What are we missing? This data provides us new material to refine our models so that our models are more accurate and account for the detail and the subtlety that we just kind of had to assume before because we had no data that would weigh in. We took the simplest model, and it just turns out the simplest model is not correct. We need more complexity in there. This is the way science happens. In fact, in the probably last 20 years that I've been paying attention, there are routinely stars that are measured to be older than the age of the universe. Clearly, that can't be right. But we don't say, oh, that means Big Bang cosmology is wrong. That means, okay, let's go back and reevaluate what we know about the age of the universe. Let's go reevaluate what we know about the age of stars. And if we're correct, those are going to eventually align up with one another. Which I might add, if you go look at scripture, there are numerous, this is how we look at scripture. We read Genesis, we say, okay, this is what it is. Then we go read Psalms, and we read Revelation, and we read the Gospels. And we say, wait a second, it seems to say this. Well, if what we were reading here seems to be in conflict with what goes on over here, we say, we need to investigate more deeply. So you go back and you reinvestigate. How do we interpret? What do we do here with Genesis? You don't say, well, we're going to change what we meant in Genesis to align with Matthew. No, you go back and you reanalyze both. And if you're dealing with a robust system that's actually getting truth, they're going to agree with each other. Well, that's what's going on as we do science. And that's what I expect will happen here with the more complex, massive galaxies that we're finding. And the last thing I would point out is that even, let's just say, if Lerner is correct, his model can explain why galaxies are more massive and more complex than what they are. In doing that, his plasma model has no explanation or no good explanation for why a galaxy that is further away from us is moving faster than us. So if I were to switch to his model, I'll get a solution to a smaller problem, but I will lose a solution to a bigger problem. And so all that to say is, no, the James Webb Telescope images don't show that the Big Bang didn't happen. It doesn't even really weigh in on that. But what it will do is, as we've got this new information, now that gives a fun playground, good fodder for scientists to now go in and say, all right, let's refine our models, get a deeper and better understanding of what's going on. So I'm fascinated by all the stuff that's come out of the web.